Thank you for the introduction, Wilma. My name is Willem Slabbert, and I am the magnetic separation specialist at Multotec. I'm here to talk to you around the MagSep and the demagnetizing coils and how they can serve in the overall DMS health as a kidney loop and also removal of kidney stones in the dense medium separation plant. The contents will cover the duty of the MagSep, what is already known, as well as the peripherals that you may not have known. The ideal operating conditions of a MagSep, in other words, the factors affecting its performance. Then there are also other factors affecting medium consumption in the plant that we should never forget. And finally, I will conclude with demagnetization, which is the purging of viscosity and removal of impurities out of the DMS, similar to what kidney stones are removed out of the body by kidneys. But first up, the wet drum magnetic separator. We all know that the MagSep is responsible primarily for medium recovery. However, it also has other functions. These peripherals include that makes the MagSep part of the DMS an integral part of the DMS is to provide an overdense medium stream for the correct medium density control. Also to purge any non-magnetic fines from the circulating medium inventory, to bleed off the degraded medium particles and to regulate the medium's viscosity within the overall dense medium separation plant. And finally, a MagSep can also provide degrit water that can be circulated in plant to the drain and rinse screens and overall save the plant water utility. Now let's look at these in more detail over the following slides. We start out with degrit water. On this side of the slide, we have the MagSep feed into the feed box, running down into the underpan where the medium is recovered in an overdense, through to an underflow tank, and in this particular version of the MagSep, it also has an added optional extra, which is called the overflow box. So this additional piece of stainless steel allows degrit water to be effectively recycled. Now this degrit water would be free of fast settling solids, and therefore is an ideal stream to be sent to the drain and rinse screens. Secondly, the MagSep is also responsible to get rid of any non-magnetic fines that are then purged to the underflow through the underflow outlet of the MagSep. The magnetic separator can provide an overdense density of an Sg of 2.8 for magnetite and 3.2 for ferrosilicon. This overdense is then circulated back to the correct medium sump and makes the overall density control of the plant easier. Finally, the MagSep is also responsible to bleed out any degraded, ultrafine magnetic medium particles to the underflow. If this is not done, the overall DMS circuit will build up viscosity. So the MagSep is therefore responsible to regulate the viscosity in the overall DMS plant. If we consider a typical dense medium separation flow diagram, where we start out with a cyclone, overflow and underflow, both reporting to the drain and rinse screen. We can see that on the rinse section of these screens, there is a dilute medium stream going to a dilute medium sump. From the sump, the dilute medium is pumped up through a potential densifying cyclone and into the wet drum magnetic separator, which is of course the crux of this presentation. So in the next slides, we'll explain how this magnetic separator, which serves as a kidney loop between the correct medium and the dilute medium circuit, how the functions of the MagSep contributes to the DMS. So first of all, at the discharge end of the MagSep, we can have the degrit water that is free of fast settling solids, and that water can directly be used as the sprays on the rinse section of the drain and rinse screen, thereby eliminating the additional water utility that is needed and ensuring overall effective water recovery within the plant. So a very simple additional extra on the MagSep can have a huge cost on water savings and utility. Next up, we have to discuss the bleeding out of non-magnetic fines through the MagSep. From our circuit, we can see that if the non-magnetic fines reports to the MagSep overdense or recovered medium, that will be returned back to the correct medium sump. Those same non-magnetic fines then would be recirculated through to the dense medium cyclone and eventually will report through again to the dilute medium sump, which is in closed circuit through the MagSep with a correct medium sump. In other words, if fines are not purged, non-magnetic fines are not purged out of the system through the MagSep, one could quickly have a buildup of these fines. Those fines would not only affect the density of your correct medium, but the fines would also affect the viscosity, which has an influence on the organic efficiency of the cyclone. Thirdly, our overdense product from the MagSep goes directly to the correct medium sump. If the density is too low, there might be an additional need for a pipe densifier. Pipe densifiers in themselves are extremely efficient, but adds one more level of complexity. If we have varying flow through the MagSep, then the pipe density also has to be carefully controlled to ensure that the correct medium density is always achieved. However, if the MagSep is performing well and the overdense density is above the cut point density, the correct medium density within the correct medium sump can easily be controlled with the addition of only water. So good performance of the MagSep with a good overall overdense density allows for easy operation of the MagSep and dense medium separation set point. Finally, the MagSep is also responsible to bleed off any ultrafine particles. If these particles remain in circuit and is continuously recovered by the MagSep, then it would affect the overall density of the correct medium. It should be noted that some fines should remain in the circuit because they assist with medium stability. However, the ultrafines in the -10 micron range should systematically be bled out of the system, which otherwise would result in viscosity and cyclone separation problems. So from these slides, the MagSep does not only recover medium, but goes on to regulate the viscosity and the density, both of which are critical parameters to the health of your dense medium separation. So in its kidney loop working in the dense medium separation plant, the MagSep plays an integral part to your overall DMS health and performance. Now the MagSep, of course, is a function of its process and mechanical performance. So let's look at the parameters that affect MagSep performance in more detail. First of all, we must have slurry level in the machine. As indicated in the diagram at the top of the screen, the red line indicates that the MagSep must have level in order for it to be able to recover the medium. Secondly, the angle of the MagSep is quite important, and the angle must be elevated above the discharge lip as shown in the red circle to make sure that the medium that is recovered onto the surface of the drum as the drum rotates is allowed the opportunity to be discharged over the discharge lip. The third important factor is the overloading of feed slurry at flow rates higher than 90 to 120 cubic meters per hour per meter of drum width. This is for a 900 millimeter diameter MagSep. For 1200 diameter millimeter MagSeps, the flow rates are doubled up. So a 1200 unit can handle 180 to 240 cubic hours per meter drum width. Now, overloading of a MagSep can occur in three instances. It could be that the complete machine is being overfed consistently. The second mechanism is that you can have partially blocked pipes or a partially blocked underpan, which then would result in sectional overfeeding of the MagSep in certain conditions. And the third mechanism is surging flow into the machine where it is systematically overloaded, but not continuously. The magnetic solids feed concentration must also fall within a specific range. The MagSep performs really well when it's being fed at between 120 to 250 grams of magnetic medium per liter of total slurry feed into the MagSep. Too high a percentage of non-magnetic material can also affect MagSep performance, and it is typically recommended that not 25% of the total solids should be non-magnetic. The machine setup and critical dimensions plays only a minor role in the effect of the MagSep. It should always be remembered that there are other factors that also affect medium consumption on a plant. In order of decreasing importance, housekeeping and leaking of correct medium in the plant, especially at correct medium densities, can quickly result in losses even though the volumetric leakage is quite small. If your floors and sumps are therefore not designed to recover the spillages of these correct medium and reintroduce it into the circuit, those spillages can easily become losses. Drain and rinse screens are sometimes also contributing to overall medium losses in the plant. Only fourth on the list is the wet drum magnetic separator. And fifth, we have the medium makeup circuit, where medium can unfortunately be lost before it is even introduced into the plant. Now that we've covered the MagSep, even though all of its advantages to overall dense medium separation health, there is unfortunately one downside to it, and that is, as soon as magnetite or ferrosilicon has passed through a wet drum MagSep, the media will typically retain 1/3 of the magnetic field strength of the MagSep. If a MagSep is running at 2000 Gauss, it means the residual magnetism on the medium is in the order of 600 Gauss. To put you in the ballpark, 600 Gauss is the typical magnetic field intensity of a fridge magnet, so definitely not a force to be ignored. This magnetization of the medium occurs after only one pass through the MagSep, and then the medium stays magnetized because of the ferromagnetic properties of the medium itself. So demagnetizing that medium is quite important. Otherwise, you would have these magnetic forces that contribute to viscosity throughout the correct medium circuit of your DMS. Now, demagnetization is very purposeful. It does not occur naturally, and it has to be targeted as an outcome in order to demagnetize ferromagnetic material. Now, that is achieved by alternating your magnetic field from north to south, and at the same time, through each increment alteration in reverse of polarity of the magnetic field, to also decrease the magnetic field intensity. In other words, if we were to demagnetize a particle that is charged at 600 Gauss in a north pole orientation, we would demagnetize it by reversing the field to 500 Gauss south pole, back to 300 Gauss North Pole, 200 Gauss South Pole, 100 Gauss North Pole, and so on. So this hysteresis effect can only be overcome with purposeful demagnetization using demagnetizing coils. There are, in the natural world, other forms of demagnetization that involves heating material to the Curie temperature, which is typically around 100 degrees and not seen within DMS circuits, or excessive beating, which of course is not often seen in DMS circuits. So the only way to purposefully demagnetize material is to alter the electron spin and the polarity of the particles to a neutral position where no net residual magnetism remains. Some practical work done by Napier, Munn and Scott online on a real operational DMS, not from sampled material, but from an in-stream analyzer in the real world, showed that viscosity decreases from 120 to 90 centipoise when a demagnetizing coil is switched on. Over the duration of the demagnetizing coil's working, we can see that viscosity continually decreases. However, as soon as the coil is de-energized or switched off, we can see that the viscosity again starts to increase. We all know that a lower viscosity will increase the separation efficiency in your DMS, particularly for cyclones, even though it has a smaller effect on DMS drums. So to conclude, both the MagSep and the demagnetizing coil are important to, in a kidney loop fashion, remove impurities from the DMS, while the demagnetizing coil is responsible to ensure a low viscosity throughout your cyclone separation process. Thank you.